So good morning again, everyone. We are going to be completing the capacitor handout today. So since it's not going to take too long to finish the capacitor handout, we'll do a couple questions. I do suggest you all have graph paper. Get at least one sheet of graph paper on you because we're going to be plotting a graph. All right, so at least, if not plot the graph, I'm going to give you guides on how to start the questions for this topic. Now, after we are finished with capacitors, I'm going to work on getting a worksheet for you all for capacitors and electric fields. Why I waited till after capacitors? Because these two topics tend to mix a little bit. They do overlap. So I didn't, let's not give you half and half of a question. We'll do a whole question. So we have capacitors, charging and discharging capacitors. Now, let's review. A capacitor is essentially a short-term battery, right? Where we have to know that it does have a polarity to maintain, and we do know why it has polarity to maintain, because we have charges building up outside and inside of your capacitor, and that's how it allows it to store charge. So at the very simplest, a capacitor is a short-term battery. This is why we use capacitors. Capacitors work in such a way that they provide current to a system when there is not active current flowing or there is variable current in your system. Why is my camera bent? I don't know. All right, so let's just continue reading through. Many electronic circuits involve capacitors charging and discharging through resistors. Now, there's always something to note. You always must have a resistor when we are using capacitors. We're going to go through why just now. The way in which these processes occur is similar to exponential change and decay. Remember, exponential change and decay means that you can always tell my board is at an angle. Anytime we have exponential change and decay, we are going to be looking at something going down in a curve. While charging a capacitor, reading from the handout, while charging a capacitor, it does so over a certain period of time. All capacitors are charged and discharged using a resistor as a limiting component. If the charging current I remains steady while charging, the capacitor will be fully charged after. Now here, we need to have a capacitor and resistor in series with each other. Why? Because the series resistor limits how much current or limits the voltage that is entering your capacitor. Remember, the capacitor has to take its time to charge up and it has to take its time to discharge. And by putting a resistor in series with it, what it has, we're going back straight to Kirchhoff's law. Since they are in series, you're going to get a V1 and a V2 happening. So that means you're going to reduce the voltage that is entering into capacitor. So that means you're going to give your capacitor more time to build up charge. And we can use just a simple mathematical formula to determine how long it takes to charge a capacitor. So our time constant, or the time it takes to charge a capacitor, it's usually not a capital T. It's a Greek letter tau, but it looks like a T, right? So tau is equal, just take capacitance, whatever capacitance you have, say you have 10 microfarads, multiply by your resistance, multiply by 4 kilo ohms or something. Usually resistors are large. Resistors are not small because we want our capacitor to take some time to be able to charge, and we want to take our capacitor some time to discharge properly because we don't want just power on and power off. That means it's not going to act as a short-term battery. All right, the whole reason why we use a capacitor, right? If we look at a graph, how it behaves, as time passes, your capacitance gets smaller and smaller and smaller. So that means it gives off current into your circuit while the power is not on. So this acts as a short-term battery supply or a power supply because it takes a while to discharge. So if we have a very small capacitor, now this is still a small number because it is micro 10 to the minus 6, we need a somewhat large resistor in order to have an appreciable time constant. So this is, really cool as in the time constant. The time it takes for your capacitor to charge and discharge really does depend on the components that you add to your circuit. And you're going to realize, we're going to encounter that more and more. Your circuits are dependent upon what you put in them and not just the nature of your components. So time constant tau is equal to CR seconds, where C is your capacitance, R is your resistance. So discharging a capacitor. We are not going to go through the maths in it because it is a little bit of differentiation. So we're just going to learn the formula. Please, those of you who have done add maths and are doing maths, give the equation a read through. All right, so what we have when we want to look at charging a capacitor, the formula that determines or defines capacitor charge is Q is equal to Q naught E, which is natural log, minus T over CR, where Q is your charge, all right, at time T. Q naught is your initial charge. E is natural log, so that's going to be on your calculator. T here is your random time. Your time of time is equal to T. And CR is your time constant or your capacitance multiplied by your resistance. Now here, what this takes into consideration.
Miss, I not hearing you.
Same here, not here.
Okay, sorry. Where did I stop talking? I just hit the mute button. I don't know why.
When they started the graph,
Okay. All right. If we were to plot a graph of charge versus time, we get an exponential decay curve because as time goes by, your charge decreases as time increases. Because what happens if we have our capacitor, as time goes by, right, electrons are fed out of your capacitor and into your circuit. So that means the charge that has built up in your capacitor will decrease over time because it's not meant to keep that charge. What keeps the charge in your capacitor is the fact that there is a current and a voltage outside of your capacitor. But the instant you remove your charge and voltage, it is going to start to decrease. Let's think about it. If you have a bucket full of water, as in the rate of the, okay, that's a terrible bucket. Right? Imagine you have a bucket of water, right? And it has a small spout, a small pipe at the end, right? And you are filling this bucket with water, a pretty good stream of water. This is your current that is coming in, right? And your current is going to be coming out of your capacitor. Imagine this is your capacitor. When I stop putting in current into my capacitor, as and I stop with this, what's going to happen? These electrons are going to continue leaking out and draining out of your capacitor until it is empty. All right, I don't think there's a simpler way to explain this. So once you put current into here, it is going to just act, all right, it's just going to continue having your current flowing through your system. It's going to flow out of your capacitors, not to say, it holds the current for a long time. It just allows the current to pass through. And the instant you take out your input current, right? It's going to continue draining out until it has no charge left. Well, no appreciable charge. So that's where we get the K curve, right? As time passes, your current is, or your current or your charge, current and charge are basically the same thing, remember? Q is equal to IT, right? Your current and charge are going to decrease as time increases until it reaches a point of 0. All right, so our first equation to learn here is Q is equal to Q naught E, E being natural log to the power minus T upon CR. Why it is minus? The minus indicates, right? The minus sign indicates that our charge is decreasing as time goes by. Now, this is our main equation for charge in a capacitor. So as your capacitor discharges, right, as time passes by, your charge is going to get smaller and smaller, right, until it reaches a small value, right? And similarly, if you look here, we know V and C and Q are related. So Q is equal to V by C. So obviously, right, Q naught will be equal to V naught by C. Why are the C is constant? Because that's the value of our capacitor. Our capacitance does not change because we're taking that component and putting it in our circuit. So capacitance does not change, but what can change is your voltage. What can change is your current and your charge. So here we can come up with an identical equation where the voltage in a capacitor does vary. Let's just make this a wee bit bigger, right? It varies exponentially, right? A negative exponential curve. So that means as time passes, so if you were to plot a graph of V versus T in a capacitor, it is also going to have a negative curve, all right? It actually doesn't look like that, it's more like that, all right? So V and I, you have identical equations because they all do decay over time. It's not to say, your current is going to decay linearly. Your charge is not going to decay linearly. Why doesn't it decay according to a straight line? Right? Why do we have a curve here? We're going to see why we have a curve. Thinking about, you all know the little experiment from Form 4 or 5 where we had our container, right, full of water with our 3 spouts. You all remember that? To show about pressure? And you all knew that
Yeah,
at the
for
very
the
top here,
can.
your stream, your water stream wouldn't be too far. At the middle part, your water stream is sort of coming out, and way at the bottom here, your stream goes the furthest. You all remember that? Should have done this in Form 4. Something
Yeah, miss, we
identical
did
here
that.
happens. What happens to get your charge, right? When you start off with your Q naught, you have your most amount of charge happening. So what happens? We have a lot of electrons to lose from our capacitor at our initial time. So what we end up getting, get a sharp decrease. And since we have less and less capacitors coming out, that means they're just going to end up having a little bit coming out at the end of the time. It does not go down in a straight line. Why it does not go down in a straight line? Because the amount of charge that you lose depends on how much charge is inside of our capacitor. Right? So it's basically like pressure. If you have a high pressure, you're going to have a high rate. This is your high rate of loss. And the less you have above you, right? So if you look here, I know it's two very different explanation analogies, but it works. When you have a little bit of charge left, you're not going to get many things coming out. You're going to get a small rate coming out. Similarly, if you all took a bag, all right, take a plastic bag. You all know this one. If you put a hole in your plastic bag, no, we're not bursting the plastic bag. Put a little hole in the bag. All right. When does it lose the most amount of water? Where's my pen? All right, so you get a plastic bag full of water, you put a little hole in it. All right, when you have a lot of water, you are going to get that water streaming out and not even obeying gravity. It's going to go where it wants to go. But when you have less and less water left inside of your bag, the pressure, the amount of water you have to lose is going to be less. So what's going to happen? You're going to just end up getting a few drops of water coming out instead. All right, so this is why we have a decay curve, because as time goes by, we have less electrons to lose. All right, so if we have less electrons to lose, the decay or the loss of electrons will be less. So that's why we end up with a curve, and it's not a linear relationship. But remember, we did go through the maths at the start of the term and how to change um, a curve to a straight line. And this is why we have to do it in this topic, because we have to know how to manipulate this equation here to get a straight line. That's going to come in our questions next. Okay. The equations show that when a capacitor is charged to a resistor, both the charge on the capacitor and the PD decrease exponentially. So when T, remember T here is any time, and your time constant tau is your C by R. Now, when your time is equal to your time constant, and we plug it into your formula, you are going to get Q is equal to Q naught e to the minus 1. Everybody get your calculators right now for me, please. Everybody. Don't just sit and say, yeah, miss, I'm a calculator when you're just watching your computer. Everybody get a calculator out, because you're going to do this for a question. You all have calculators? Please identify your e to the x button. It is the second function of your ln button. Can you find your ln button? Ln is just a ln. Find our ln button, and I want you all to go and work out how much is e to the minus 1. So what you're going to do, if you want to know how to plug that into your calculator, you're going to do your EX button. You're going to do your negative button. Remember, your negative button is not your addition and subtraction button. We went through this already on how to get your negative button. So you're going to do e to the x, your negative sign, not the subtract sign, your negative sign, and 1. Hit equal, tell me what you'll get. Point 3. Actually, you want to do to 3 decimal places here. You will get 0.368. Did everybody get 0.368? Yeah, anybody did not get 0.368? Okay, silence means yes.
Miss, you could say it, but
So
we have
what is this actually
calculate,
telling us?
please.
Why did we just go through this? When your time is equal to your time constant, remember we said time constant, tau is equal to C by R. So we can work out what your time constant is simply by multiplying the capacitance by your resistance. All right, so when your time is equal to your time constant, your charge on your capacitor would have reached to 36.8% of the initial value. Now, this is going to come in really handy when we have to do our capacitor labs. Just please note after whenever, if we have our time constant, and we could always work out our time constant, when our time is equal to time constant, our charge will be 36.8% that of the initial charge. So somebody, just think about it. Somebody can tell you what is the initial charge. They can tell you the final charge. They can tell you what the capacitance, and then they're going to ask you to find out what is the value of the resistor connected to your circuit. They can do this because they know, right, when time is equal to your time constant, we are going to get our charge being 0.368 that of the initial charge. So this is an important topic to note. All right, when you have time at your time constant, you're going to get 36.68% of the initial charge. Let's just do some further maths and check something. If time is equal to 2 time constant, all right, remember time constant is just the amount of time it takes to charge your capacitor. It usually takes longer to discharge your capacitor. Let's write that down. All right, time constant is equal to the time to charge your capacitor, and to discharge your capacitor is more than your time constant. It takes a longer time to get rid of that charge on your capacitor when you are discharging. Now, of course, when we do a lab, there's a very easy way to discharge a capacitor. There's an instantaneous way. Think about if I had a time constant, if I had a capacitor, all right, where our capacitance is 4 millifarads, and our capacitors are around 4 millifarads, 3 millifarads, and my resistor was 100 kilo ohms. Anybody want to tell me how long this capacitor will take to discharge, considering time constant is equal to CR? So tell me, how long will this take to charge? All right, if your capacitor is 4 millifarads and your resistor is 100 kilo ohms. You all got 400? All right, you just multiply the two numbers to get your 400.
Yeah.
All right, so it's quite easy to work out your capacitance and your discharge and stuff for these things. Just to give you a little tip, no, actually I won't give you a tip on how to discharge the capacitor easy in a lab because you won't remember it. I'll tell you when we have the capacitors in front of us. All right, so that's it for this topic. All right, passes actually is a short and sweet questions. Before we go on to the past papers, we're just going to work out how does reach here.
0.37 or 0.368.
Are you all playing over my recording? All right. Now we didn't do questions on how to do series.
Like the key, you mic on.
Oh.
You know, we watching on the TV, they can even listen to it.
No, his mic is off now. All right, his mic is off. All right. So we didn't do some questions on how to find your capacitors in series and parallel. So we're going to do some quick rapid fire questions on that. All right, find C total. All right, really quick and fast. So if I wanted to do question 1, where I have my not resistance, my capacitance being 4 microfarads and 6 microfarads. Since we are allowed to use calculators, let me save you all the headache. If I were you for part A, we're using our calculator straight. What we would do, just go, this is what you all can do. You can do 2 ways. You can just add the numbers, but I don't suggest you add the numbers because you can make mistakes. Let me just check. All right. So what you can do, since both of these are in microfarads, right, we can just go and say 1/4 plus 1/6, and then we find the inverse of that. So, just do the 4 to the -1 on your calculator plus 6 to the -1. You hit equal, and then your answer, you hit the minus, x to the -1. Tell me what you get. Right now, tell me what you get. Using the x minus 1 function in your calculator. So you have the shortcut ways where we can just take the number and work with the numbers, since we do have the same unit being used. Now, if we had microfarads and millifarads, you have to go and use your numbers properly. But since we do have them all to the same base, Take your mic off, please.
I get.
Since we do
Nah,
have
I was
them,
just like, I get it now.
okay, that's good. All right. Since we do all have them to the same base, you all could have just gone and add the numbers, just like how we do in series capacitors. It's 1 over the value, and then you find the inverse of your answer. Right? Or you could have gone and done the long way. Either way, I actually did the long way both ways just now, just to make sure that it was working out fine. Because sometimes you cannot do shortcuts in these questions. So if you want, you could have done the 4 by 10 to the minus 6. You hit the -1 and button on the calculator. Do the 6 by 10 to the minus 6 to the -1. You get your answer, and then you hit to the x minus 1, and you should get your 2.4 by 10 to the minus 6. You all try that. Make sure that you get the same thing no matter what. Question B is really simple. You have two capacitors in parallel, and when you have parallel capacitors, all you're going to have to do is just add up your values. Part C, we have a combination question where we have a parallel set of capacitors in series with another capacitor. So what do? We work out the parallel section first. Very simple. Parallel section, you're going to have, for C, you're going to have 4 plus, let's put this down. 4 plus 8 in parallel is just going to add up the numbers. So you're going to get this working out to give you two 12 microfarad capacitors in series. Please, y'all don't make this mistake. Hey, look, we have 2 in series, so we'll get 24. Because that will not work, cannot work, because when you have capacitors in series, we have to go through the method of calculating 1 over your value. So we can make life easy, since we do have the same unit or the same index here. All we need to do is find 1 over 12 plus 1 over 12, and then your answer, you're going to find the x minus 1. Or even simpler, 6. Very good, Tristan. 6 is correct. You can find 12 to the minus 1 plus 12 to the minus 1, hit equal, and then you do your x minus 1 function and answer, and you will get 6 microfarads. Please remember to put in your units. Don't just leave it out, because units are important, and especially when you don't do your answers properly. Did everybody get 6? Actually, since you're the one to say when you get something, anybody did not get 6?
Mas aí você já quer.
Okay.
Baixa aqui.
All right, clearing up the board for part question 2.
Yeah, I guess 6.
Good, great. Anybody did not get 6? I want to move on to the next question. We're going good? Everybody? Okay. All right, so you are given not 4 capacitors, 3 capacitors. I don't know why I didn't write the 4th one. 3 capacitors. One capacitor is 1,000 microfarad. Next one is 4,700 micro, and next one is 2,200 micro. I did not just randomly choose these numbers. These are the capacitors that we have in school. These are capacitors that the lab exams were written using. So they're very common capacitors. And we asked you one, which combination of capacitors will give you a capacitance of 3,200? Now let's just clear it up here. What is going to give me 3,200 when I add up my capacitors? Now here, sometimes you have to do it, so you're going to have to kind of work backwards. All right, so I have 3,200 microfarads, and I want to use 1,000. Now I don't have to use all that. I have 1,000, 2,200, and 4,700 microfarad capacitors. Which of these two, which of those will give you 3,200?
Miss the 1,000 UF and the 22
Not UF,
100
microfarads.
microfarad.
Farad. Farad is singular, farads is plural. Okay, so the 1000 and the 2200 will give you 3200, but in what orientation? Will those two capacitors be series or will they be parallel?
They will be parallel.
Very good. Because we know we add up capacitors in parallel just to add your numbers to give you your answer. So you're going to get the 1000 plus the 2200 microfarad capacitors. So looking at that, what is the next one? The next one is 7900. Which two is going to give me 7900? And in what combination? What two or what three actually? Hint, we're using three capacitors.
3 in parallel.
We will use the three of them in parallel. So we'll have the 1000, we'll have the 2200, we'll have the 4700. All right, so that is for that one. Let's look at the next one. Was the next one 1500? 1500 microfarads. Tip, we are only using two capacitors. Now we just added up our capacitors in parallel. And if we look at this, 1000 plus 2200 is 32, 1000 plus 47 is 57, 22 plus 47 is 69,000, 69,000, 6900 microfarads. So obviously we're not going to be in parallel, we're going to be in series. We want to use two capacitors in series. You all go ahead and try and see which capacitors in series will give me 1500. So let's look at our combinations. We can take 1000 and 2200. We could take 2200 and 4700, or we could take 1000 and 4700. Try those three and tell me which one you'll get. So for the 1500, all we had to do was to add up the two of them. Now it sounds like a long method, but what you're going to do, you actually have a lab in school where you are given various capacitors and you have to come up with combinations to give you a certain capacitor value. All right, now, if it's a lab, that's good for your AI. So here we can just add the 47 minus 1 plus your 2200 to the minus 1, and then find your x minus 1 of your answer, and you will get, well, okay, 1498, which is about 1500. Last one, which is the last one, which is how much? I think 800. Sorry. Or 600. All right, now, if you were to look at this, when you have more capacitors or big capacitors in series, you'll get a small capacitor as your answer. These were we rationalizing out. So if I took my two largest capacitors just now, 22 and the 4700s, and I got 1500, that means I have to get an even bigger or a larger amount of capacitors to work out the 600 microfarads. So anybody wants to throw a guess as into which ones we are adding?
All.
Oh, very good. Great. All right, and when you add all the capacitors in series, you are going to end up getting, well, really close to 600. Now, this is why I like to use the x minus 1 function in your calculator, because we don't sacrifice accuracy by rounding off your numbers. If you have to round off your numbers here, especially in these topics, you're going to have a big difference in your answers. So everybody okay with these? All right, we're going to get a few more questions where you are going to get circuits. You're going to get your capacitors. You're going to have to work out your charge and your current and all of those things in there. Okay, so let's take a look. Class is over, but let's just take, a few minutes just to go through the exam questions. I'm going to send you these questions in the group, well, in the page, so you can take a look at them. So I have put for you all 2008 and 2010 capacitor questions. So let's read them through. When a capacitor discharges through a resistor, its current at any instant is given by the equation of I is equal to I naught e to the minus T upon RC. Using this circuit in the figure 1, a student collected data to plot a linear graph from this function. So what he did, the student had a microammeter. Our resistor with our capacitor is 68,000 ohms. We don't know our capacitance, and our PD is 3 volts. So let's tell you how this circuit will work. All right? What's going to happen when I want to put on and when I want to charge my capacitor? All I do is just take my switch and switch this on. And what's going to happen? My current is going to pass through this part of your circuit, and it's going to build up the charge on my capacitor. So this is my charging part of my capacitor. Now, when I want to discharge my capacitor, I have to remove it from the power supply. So I have to disconnect it from the power supply. So all you do in a situation like this, you just take your switch and you move it over to the next side. So that's all you did. You just went from one direction and you take your switch to move to the next. And what happens by moving it across to the next side, we are now discharging our capacitor, and our capacitor is now going to have current just moving around in this section. Remember, this section is now open, so no current is going to flow through this section once that part of the circuit is open. So what's going to happen? Our capacitor is going to discharge over time. The ammeter here is going to read your current as it gets smaller and smaller, because remember, as your capacitor discharges, it loses its energy and it gets smaller and smaller. All right, and it passes through a 68,000 ohm resistor. So let's look at this here. In the space below, write a suitable linear equation and then complete the table so that the straight line graph may be plotted. Please note, all you're going to be doing is converting your number and you're finding the ln of that number. There's no need to go and find ln wait a minute. That's nonsense just now. Okay, yeah. All right, so you just go and find ln of your raw number here. So you find your ln of your 36 to 2 decimal places, ln of your 30 to 2 decimal places, and whatnot. I had shown you, and we went through how to convert linear exponential graphs into linear graphs earlier in the term. Wasn't this the first thing we did?
I can't remember.
Go and revise it. All right?
Yeah.
All right, I know we did go through this at the very beginning of the term. All right, so you're going to put your equation of I is equal to, ln I is equal to whatever plus whatever. You're going to plot a graph of ln I versus t, and you're going to find your curve, and from your curve, just plot your curve. No, plot your straight line, I mean, and you're going to get your graph. Question 3, or the next question that I have up here, is from 2010. All right, these are 2010 question. I'm going to put up the questions in the group, so don't worry. Define capacitance, calculate your PD and your energy stored. It's the same exact thing where we're charging and discharging our capacitor. All right. You're going to get a graph where you can read off your voltage as time changes. As time changes, your voltage is going to decrease. So from this, you're going to have to read off your time at given points. So if your time is 15, you're going to find 15 on the graph, read off your value. If your time is 90, you're going to find 90 and read it off from your graph. Then calculate 1 over V and plot your graph. Where is the graph page? I will put in the full question in there, the 2 full questions, and you all will do them out and see how well you get. All right, I will post up the solutions right afterwards, so you'll see what you got from doing the question. So we are finished with.
So if we happen to score load, this is for going up from course of maths.
Not this
Okay.
one, right? Not this. These are practice questions. The worksheet I'm going to be putting up. All right, I think I still have to send out a couple marks or a few things. All right, but we're going to put up a worksheet with electrical fields and capacitance, since those 2 topics do meld with each other sometimes. All right, so I'm going to post up a few of those where you're just going to give out the answers. Now, if you got your answers wrong, your working would have been wrong. Okay, so this is kind of working on the premise that we might have multiple choice paper next year, but it doesn't look so. It looks like we're going to have full exam and school from January. Okay, all right, so you're going to get those in the Google Classroom. Let me stop the recording. So that's it for the class. That's